Hello, I'm Marcelo Ang. I'm with National University of Singapore. I'm happy to share with you my thoughts and our work in robotics, specifically in unstructured and human environments or in our everyday life. This is especially useful in today's COVID-19 pandemic situation. And I hope through robotics science and technology, we'll always be in startup mode, no matter how established or even for us as startups, that we can always have the innovative spirit to keep reinventing and creating new innovative things. So let's look at science and technology and how it has affected our quality of lives. The first Industry 1.0 is the invention of tools like gears, pulleys, levers to amplify our muscle power from our hands, right? Using mechanical advantage. Then came about the invention of steam power and later on of electricity, so that these tools, pulleys, levers, wheels will be turned by electrical power or steam power, no need by muscle forces, human hands. Then came the birth of computers, and this gave birth to robotics and automation, where the computers will create the programs or will run the programs to make the links of the robot move. These robots move in structured environments where the infrastructure is fixed and there's human robot separation. Today, Industry 4.0 is really taking this further into autonomous robots, from factory automation to autonomous robots working in our homes. And instead of structured environments, it will now be in unstructured environments. The infrastructure environment is not fixed by dynamic. There's no complete information, known information about the environment. And there is a mixture. Humans and robots work together in everyday life. In other words, the robot is our ultimate tool, our ultimate human companion to help in our everyday lives. So how do we go from this situation, robotics automation, to robots to everyday life? Notice here, you have the robot welding a car. It knows exactly where the car is. So it doesn't have eyes. It doesn't need eyes. It doesn't need external sensors because it will know exactly, it knows exactly where things are. So structured environments, exact, it can do it blind. It just needs to feel its joints. By feeling its joints, it knows the position of the end of its hand and doing welding, for example. Bring this to everyday robotics means how do we move this from a factory environment where the human and robot are separated for safety reasons. As a matter of fact, this robot on the left is in a cage, right? When the cage opens, the robot shuts down. How do you go to shopping malls, our grocery aisles, our hospital wards, our homes, our schools, our parks? So everything else on the right is our environment except the factory. So rather than structured, it's now unstructured. Rather than human-robot separated, there is a close human-robot interaction. So the challenge is really how do we move from factories designed for robots to factories or intelligent autonomous robots adapting to spaces which are designed for humans. As human beings, I don't want to compromise how I live or change my home environment because the machine or the robot will help me, right? I want the robot to adapt to this environment. So what are the gaps in this? Yeah, there are mainly many gaps divided into two kinds. One is we need a better body. Can we move from the typical industrial robot like the KUKA KR60 to something like fluffy, like Baymax on Big Hero, something cute, lovable, that's able to work in unstructured human environments because it's lovable. Humans are more affectionate to it, are more open to working with it. And even if it makes mistake, it doesn't hurt you because its body is soft. We need a better mind, right? Traditional programs like flowchart of doing things. And another way of doing things intelligent is learning from experience by imitating how people do. or doing things by trial and error. And these kinds of intelligence, there are two kinds. If I grossly divide it in two categories, the low-level intelligence, or I call reflex action, and high-level intelligence, where there's higher level decision making or maybe cognitive processes. A better body, a better mind, all come together to create a human-centered robotic manipulator that will help us as human beings in doing our everyday life. And two important questions are as follows. What is the right level of autonomy, right? Some people say that robots will replace human beings and they're afraid of that, right? I think that will never happen because there's still, a human is still needed to turn on the robot or to turn it off or to do some form of supervisory level control. So there's a level of autonomy that the robot does, but the highest level is still human is in the loop, right? But perhaps really in the very, very distant future, maybe one day the humans will really no need to turn the robot on because the robot knows when to wake up itself, right? Second question is, how do you collaborate? This is an important question. How do you teach a robot what you want it to do? And how does the robot ask for help? So these are things we do for granted. If you have a new team member in your group, the two of you will do a project together or do a job together, right? Somehow you learn how to collaborate as you continue to work with each other. But how do we learn how to do that? If we think about it, it's not so easy. And we don't know how to do it, but we expect robots to be able to do it. But it's kind of hard, right? But maybe the key is trying to find out how really our human mind works. And that's why there's a lot of interest in neural networks or the brain, right? The brain somehow has some magic of learning to learning from experience rather than doing it in a flow chart or traditional programming method. So there's a lot of work for all of us to do in all these two areas, a better body and better mind, and how this robot with a better body, better mind can work best with human beings, right? So these are the gaps we have to work on. And I will show you now in the following slide some videos of some of our work that I call mechanical intelligence. On the upper left here is inspired by a swivel chair. Our swivel chair has an offset caster. Now, if I put two motors in one wheel, by the relative velocity of the two motors, we can have omnidirectional motion. And it's interesting, this offset in the caster wheel, the offset between the steering axis and the center of the wheel creates the moment arm that provides this robot omnidirectional motion without any kinematic singularities. On the right, upper right is silicon with fabric on it and some orange cotton threads embedded in it in such a way that when air is pumped from the top, right, the finger moves accordingly, according to the design. So you pattern the fabric, you pattern the stiffness of the wires, the density of the cotton threads, not wires, so that it has variable stiffness along different parts of the finger. This on the lower right are pouches of air in series, like small little joints. It's almost like small elements, discs that are air, small balloons. By powering the balloons in sequence, this can form a finger. On the left is a 3D printed thermoplastic urethane, again by pumping air, and it changes according to its shape. So there's no active control except pumping air and maybe regulating the air pressure. So this is passive, but it has some kind of intelligence by design. But at the same time, it's stupid because it always moves the same way. It always coils, it always curves. You can only change how much it coils or curves by the air pressure. You can also achieve what's a kind of soft robot also using electric power, right? This is a double-sided tape, a dielectric elastomer here. Once electric charges or electric field across this elastomer, the elastomer is compressed and expands in surface area. It